So this is a first in a series of video lessons, tutorials, and the theme of all of these is something I haven't ever done before, which is how to teach math. I've done videos about certain topics in math. I've done blog posts about statistics in education and my feelings on them, but the thing that I do every day in the classroom, and something I've been working on for 30 years, is how do I actually teach math? So this is the audience for this would be math teachers, new math teachers especially, because I find in having mentored a lot of new math teachers, there are certain things that an experienced teacher does out of instinct, and that new teachers they're not even aware of these things. So I'm just going to see how these go. These are going to be long, and it will take a lot of patience to watch these. But I want to do it, and I hope that it helps some teachers, and those students get helped because of that. I'm just going to pick a topic. Topic I was thinking of, something from Algebra 1 that everyone can relate to. In every Algebra 1 curriculum, this topic is taught for several weeks, and the topic is systems of linear equations. I would say that in an Algebra 1 course, this is a topic that is taught for a month, around there. So a lot of things you can do with it. And I just want to take you through, let's just say someone told me I have to go teach this topic, and they're not giving me a textbook, and I have to create lessons, I have to create a unit, I have to create individual lessons, I have to create homework assignments, I have to create quizzes, I have to create a unit test at the end, maybe I have to create some kind of project to do, and I have nothing. I don't have a textbook, I don't have the internet. How am I going to go ahead and do that? Well, I might make a list of certain questions I want them to eventually be able to solve. So I would like them eventually to be able to solve questions like 2x plus 5y equals 15, 3x plus 7y equals 25. A question of that sort. So systems of two equations, two unknowns, like that, where we have to do the elimination method. That's definitely something I'd be pretty happy if students can answer a question like that. I think I'd also like them to be able to apply systems of equations to questions like word problems. There are 100 animals. Some have 2 legs. Some have 4 legs. If there are 240 legs, how many of each animal are there? Definitely, if my students can do these sort of 2 questions, I'll feel like they've gotten the idea of systems of linear equations. But I'm not going to start with these 2 questions. These are 2 questions that I'm going to get to eventually. I think I would start this by just getting the idea of a 2-variable equation. So compare that to a one variable equation. A one variable equation is like x plus 5 or x plus 6 equals 10. A one variable equation has a solution set. In this case, it's the number 4. 4 is the one and only number that makes this one variable equation true. Now a two variable equation would have an x and a y, like something like x plus y equals 10. And I would want to spend, I think, a day just getting the idea that a two variable equation has a solution set that's much more complicated than a one variable equation. One variable equation, the solution set is going to be usually a single number. Two variable equation actually has a lot of answers. For instance, since 1 plus 9 equals 10, the ordered pair 1 comma 9 makes it true. 9 plus 1 equals 10, so 9 1 is another, it's not the same ordered pair, it's a different one, also makes it true. And 2 8 and 4 6, and there would be so many, even something like negative 2 comma 12, I was going to say dot dot dot. So I would want to spend a day getting the idea of a single two variable equation and how we could find a solution set to a two variable equation. I'm feeling like that would actually be day one of my unit. So day one, what is a two variable equation? In New York, we sometimes call this the aim, and the do now, which is sometimes called the focus activity, it's sometimes called the warm up, whatever you call it in your state. There would be some kind of question. Now, the warm up question, sometimes a warm up question is some question that students don't yet know the answer to, and they're going to learn the answer to at the end of the lesson, or even at the end of the unit. I like to make my warm-up question something that kind of plants a seed. So I'll make two questions. I'll say, so kids aren't like intimidated by symbols, I'll say square plus 4 equals 10. And I'll say what goes in the square. What goes? And question 2 would be square plus, I don't want to do another square because they might think it has to be the same number. And I'll say what goes in the square and the triangle. This would be a really good warm-up question, focus, do now question, because the first question is sometimes called convergent. There's a single number, so that one has the answer 6, and every kid feels good, gets a question right. But then question 2, people start getting a little bit like nervous, like, wait, is there just one answer to this question? Can I do 6 4? Yeah. If I did 4 6, would that be the same answer or a different answer? I don't have 4 6 maybe, I have 2 8. So this is a really good question because it makes everyone think like, wait a second, does 6 4 and 4 6 count as the same answer? How many answers are there to this? Am I allowed to use, fractions? Things like that. This is a really good second question for the warm-up because no matter where the student is, they're going to be able to like think about multiple answers. Then you could have them like talk about the answers, and you're 10 minutes into the first introductory lesson on this. This is just day one. I don't yet know how many days this unit's going to be. I'm going to guess it's going to be about 10, if not 15. So it's a pretty big topic. But that's good for the warm-up on day one. Now I would start getting into the lesson. And I would use that example from before, x plus 4 equals 10, and say that has a solution set. And that some numbers make this equation true, like 6 plus 4 does equal 10, but 5 plus 4 does not equal 10. So we'd say that 4 is in the solution set, but 6 is in the solution set, but 5 is not in the solution set. So in the solution set, really there only is one number in the solution set. It's a set with one number in it. Then I would go to my x plus y equals 10. And students would now wonder, okay, well, 6 plus 4 still equals 10, but what does that mean? Does that mean 6 and 4 are numbers in here? Well, this sort of equation with an x and a y has in its solution set not single numbers, but ordered pairs. So we introduce what the concept of an ordered pair is. So an ordered pair is two numbers, they're in order, so 6 comma 4. That's an ordered pair that makes this equation true. And 4 comma 6 is another ordered pair that makes it true. And 2, 8, and 0, 10, and so on. Now, when the equation is simple, like x plus y equals 10, it's pretty easy to make the solution set. Maybe I would also throw in something like x minus y equals 2, just to get a feel for that, because that one has 6 and 4 as part of its solution set. 6 minus 4 is 2. But that one does not have 4, 6 in the solution set, because 4 minus 6 is not 2. So unlike before where 6 and 4 was in the solution set and 4, 6 had to be also with the x plus y equals 10. In this one, switching around the numbers, it's no longer in the solution set, but 7, 5, 8, 6, dot, dot, dot. So there's an infinite number of solutions to that. And so I would ask a question like, find 3 ordered pairs in the solution set of, maybe I'd go like this, 2x plus y equals 10. And we can do some tricks, like for instance, I could ask if 1 comma something is in the solution set, what would that something have to be? And then you kind of look over here and say, well, if x is 1, 2 times 1 is 2. So y would have to be 8, so 1 comma 8 is in the solution set. And we could mess around. Could I just pick anything I want for x? Well, let's see, if I put 2 in, I would get 2 times 2 plus y equals 10, or y equals 6. Maybe I start getting the idea, figure out that if I put 3 in, when the x went up by 1, the y went down by 2. Here the x goes up to 3, so maybe the y goes down to 4, and that does work. 2 times 3 is 6, plus 4 is 10. You might wonder, can we go the other way around? Can I pick a value for y? Like if I said y has to equal 2, well, if I put 2 in for y, 2x plus 2 equals 10, 2x equals 8, so I could start with a y value. Now with x, I could kind of pick any x value I want and have no problems, but with y I have to be a little bit careful. Because what if I make y, what if I try to find one that has y as an odd number? It's not that it's not allowed, but now it would be 2x plus 5 equals 10. I can solve that. Subtract 5 from both sides, x equals 2.5. So again, there are an infinite number of answers, and we can ask students to find 3 values, or I could say fill in the missing numbers, 1 comma blank, 2 comma blank, blank comma 6. Things like that. Actually, 6 isn't the best answer because it's already used in this example, in this one. Anyway, I want my first day to be students getting comfortable with the concept of the 2-variable equation and how there's multiple answers in multiple ordered pairs in the solution set. But not every, just because there's an infinite number of things in the solution set doesn't mean every ordered pair possible makes it work. Most ordered pairs don't make this equation true. If I try like 5 comma 9, that's not in the solution set. I might make up a little question, like a multiple choice question. Which is in the solution set of 3x plus y is equal to 10? Let's say I want the answer to be C. So I'll make up, let's say 3 comma 1. That's 9 plus 1 is 10. And then I can say like 3 comma 3, 3 comma 2, 3 comma 0. Now I have a nice little multiple choice question that only a student who understands the concept of solution set and how some ordered pairs are in and some ordered pairs aren't is going to be able to get this answer. This would actually be a pretty good homework question also. If I was starting to do a homework, make my homework assignment, probably make up a couple of these. I would start with those actually. Then maybe I'd go a little more open-ended. This kind where I give them one coordinate, ask them to find the other. Then maybe totally open-ended, find 3 ordered pairs that make this equation true. That would probably be plenty for one 40-minute lesson. So I have day 1 kind of planned out. Homework assignment, everything. This might not seem like a lot of material, but I promise you this is a good amount of material for one day. The concept of the 2-variable equation. So what's going to happen on day 2? Now, you have to make a decision in this unit. Do you want to get graphing involved? Have you already taught graphing yet? If you haven't, this is a good time to put it in. I am going to put it in. Graphing. This might turn into a 15-day unit now, but this is how you build up your lessons. Graphing solution sets to 2-variable equations. Aim. Some people like their aim to be in the form of a question. So, how do you graph solution sets to 2-variable equations? Now it's a question. Let me start thinking a bit before I start. I know what my aim is, but my goal of this lesson is for students to be able to take an equation like x plus 2y, or what did I have over here? 2y plus x equals 10, and to create some kind of a graph like that. That would be pretty good. If they can do that by the end of lesson number 2, I think that's a good thing. It's kind of like in lesson number 1, we encountered, is it 2x plus y? Yeah. In lesson 1, we encountered questions like this, and we found solution set. In lesson 2, I'm not going to really talk about lesson 2. In lesson 1, I'm just going to bring this up. I'm going to deal with graphing, though. Well, I am going to talk about it. So sometimes you don't want to confuse things by making the whole lesson depend on the earlier one. Sometimes you teach it separate, and then you kind of link them later. But okay, so here's my goal. I'm happy if students can graph, if they have an equation like this in this sort of standard form, and they can graph. This is actually pretty big for one day. You'd have to decide how much you want to do, because this on its own could be a 4 or 5 day thing. What I'm calling day 2. Let's just see what I would do with that. I think 2x plus y equals 10. I would introduce the idea of putting the solution set into a chart and finding this is the list of the ordered pairs in a chart. So when x is 0, 0 plus y equals 10, y must equal 10. When x is 1, it's 2 times 1 plus y equals 10, that's 8, and this is going to go 6, 4, 2. Now, this is a way of listing out the solution set. In lesson 1, we wrote it out like this, horizontally with ordered pairs. This is implying the ordered pairs. Let's see, am I able to get a little graph grid going? That's good. Can I get a smaller grid? Even better. So then I would introduce, here's a little graph paper. So here's the coordinate grid. This is x axis, y axis. And I would say, what would happen if I took the 0, 10 and graphed the point with coordinate 0, 10? 1, 2, 3, 4, 5, 6, 7, 8. It's up here somewhere. And then if I graph the point 1, 8, it's over here somewhere. And 2, 6. This grid is a little small for my eyes. 3, 4. Anyway, with better graph paper or better eyes, these points would seem to fall onto a straight line. And on that line, we could write the equation 2x plus y equals 10. Now on this line, once I connected those dots together, the dots represented 0, 10, 1, 8, 2, 6, 3, 4, 4, 2. When I connect the dots, I end up with a smooth line, and that line doesn't just have these 1, 2, 3, 4, 5, 6 points on it, but has an infinite number of points. And I could ask, like, is the point 5, 9 on the line? Well, maybe, maybe not. Like it's somewhere over there, but maybe it just misses the line. But if you test by putting 0.5, 0.9 into this equation and seeing if it makes that equation true, 2 times 0.5 plus 9 equals, I hope, 10. 1 plus 9 is 10. 10 is 10. So yes. So now the question, like, is 0.5, 9 on this line can be answered because it's the same answer to the question, does the ordered pair 0.5, 9 make this equation true? So I would have students, if I were in my lesson, I would make some more two variable equations and have them make a chart and have them turn the chart into a line. And it's a good discussion question here, like, why does something like this have to be a line if it's like 2x plus y equals 10? Why is it a line? That's a really good thought-provoking question, because it's at least conceivable that maybe the dots don't make a line, but they will, at least in this case. And I guess it would be great if some student were to say, well, when x gets bigger by 1, y has to get smaller by 2 to make up for it. Because if they're going to continually add up to 10, as 2x gets bigger, y has to get smaller, but every time x goes up by 1, y needs to go down by 2 because the x got multiplied by 2, so to make up for it. And incidentally, I really like standard form, things of the form, like ax plus by equals c, because I like this idea of, as opposed to slope-intercept form, which has its own purposes, but I do like standard form as a way of getting a feel for two variable equations. I like the idea 3x plus 2y equals 10, and the idea that if I could find some number that makes this true, like 2 comma 2 makes it true, but if x goes up by 1, y is going to have to go down by something in order to keep it true. It's a little harder with certain equations, but I really like this 3x plus 2y equals 10, or like 5x minus 2y equals 1. Usually you can make it so it's easy to find one pair, like 5x minus 2y, 1 comma 2 makes it true. 5 minus 4 is 1. But then, like, asking what happens when x goes up by 1. Well, now x is 2. Well, there's a minus here. So when x goes up, unlike when there was a plus here, and when x went up, y had to go down to compensate, so they would continue to add up to 10. When there's a minus here, when x goes up, y also has to go up. Otherwise, they're not going to have a difference of 1, right? If the difference is 1, when one gets bigger, the other has to get bigger also. In this case, when x becomes 2, this becomes 10. Hold on a second. Yeah, so 2y would have to be 9, so it's 4.5. So it's not so obvious that how much it had to go up by. Anyway, these are like good things to think about, I think. Oh, and seeing what the graph looks like. You actually only need 2 points, 1 comma 2 and 2 comma 4.5, if it's going to be a straight line. So I think for day 2, my plan would be to have them do questions like 2x plus y equals 10, or 2x minus y equals 1, things like that. Things of the form ax plus by equals c, or ax minus by equals c. I would try to make up some that there are certain ones that are easier than others. Certainly if there's a variable coefficient in front of both the x and the y, that makes it a lot harder to just make up a bunch of pairs. So I think I might do a bunch where only one of them has a coefficient. So I might do x minus 3y equals 1, or x plus 5y equals 10, things like that. I might do a bunch that either have, here I have 4 different cases. I have a plus where the y is 1y, a minus where the y is 1y, a minus where the x is 1x, a plus where the x is 1x. You could probably do a whole day just on this case, on these 4 cases. And then if you want to throw in a 3x plus 2y equals 10 to get a feel for how that works, we're going to create the graphs for these. Honestly thinking, depending on how my class is, how fast they are picking some of these things up, how much they might know already, I might make day 2 just these 4 types of questions and creating solution sets for the graphs of them, and sort of making observations about like whether the lines that come out are sort of going down from left to right or going up from left to right, or are they steep or are they shallow. Anyway, these are all things to think about. So if you look, and I'm going to end this video, I want these to be about 30 minutes each. What I've done in this video so far is started with a topic that I need to teach, systems of linear equations. But they can't master system of linear equations until they have mastered the idea of a single equation with 2 variables in it. So I wanted to do a day of sort of the concept of the 2 variable equation and the solution set and the ordered pairs. And day 2, talk about graphs, that this is a graph of the solution set to this equation, and any ordered pair that makes this equation true is on the graph, and any point on the graph corresponds to a ordered pair. This might be 3 days, honestly. I know I have it called 2 days. I might have to spend a day, maybe day 2. Maybe day 2 is just the concept of the ordered pair and how it's on the graph, and vice versa. Maybe day 3 is where I really concentrate on these 4 types. Depends how tight my curriculum is, but I'm open to the idea of making this sort of 3 days so far in the unit. You might say, well, I don't have enough time to do this in 3 days. Well, guess what? If it takes 3 days and you try to do it in 2 days and they don't learn it, you're then going to spend another day trying to review it really fast. So it's still going to take 3 days. It's just going to be 3 days where the third day, half the class is still confused because you're trying to teach it really fast and they didn't understand it so well when you rushed it through 2 days, so they're definitely not going to get it so well when you try to rush it again through 1 day. And some of the class already has it, so they're bored. That third day is going to be not fun for anybody. If it takes 3 days to teach it, you teach it in 3 days. Again, I'm not sure. This might be a 2-day thing. It might be 3 days. I might start teaching it and in my lesson see how it's going, sort of be prepared for the possibility that just this concept of relating the line to the system of to the equation, I'm open to the idea of only getting to that point. So I might plan my lesson and have like an activity that I might have an activity right here. And if I only get to this point, if I see there's like 20 minutes left in class and I'm only to this point, I might do this activity based on this thing. The students won't know, hopefully, that I was planning to do a big lesson that was going to go further than that. But if I assume I'm going to get all the way through here and I make my activity only on this stuff, I'm kind of trapped then. I don't have the option of sort of bailing out on the lesson. So a good rule of thumb is to, if you haven't taught a lesson before and you have a feeling you might only get through half of it, it's better to get through half the lesson and have an activity based on the first half than try to go through an entire thing and have they won't even have time to get to any activity. So that's a good rule of thumb also. Okay, that's all I want to do for today. Again, this series of I'm hoping this becomes a little more interactive, where like people start like sending me questions. Can you tell me how you would teach quadratic equations? Or someone might send me a lesson plan. What do you think of this lesson about statistics or whatever else you're trying to teach? I would like this to be interactive. There's a pretty small group of people that are still watching this video at this point. It's already been over a half hour. I could talk for 10 hours just about how I would teach systems of linear equations. And I think it's possible that that's what's going to happen here. So see how that goes. But for now, I've shown how I could get at least 2, if not 3 lessons, and I haven't gotten anywhere near systems of linear equations yet. But I have 3 days of teaching ahead of me, nonetheless, maybe 2. Okay, I'll see you at the next video.